Hey guys, so in this video we're continuing looking at simultaneous linear equations and finding solutions to them for a number of solutions. So finding the values of different variables such that there are a certain number of solutions to two linear equations. However, in this video we're going to be looking at a matrix method. So this is another method for calculating the solution. So what I find is whichever one you've learned and you feel most comfortable with, then go with that one. So the previous one we had like the y equals mx plus c, and we looked at the gradient and the translation. But now we're going to set up a matrix and then look at the determinant. So with this method, rather than setting up the equation like this, y equals mx plus c, we want to set up the equation so that we have ax plus by is equal to c. So we want to set it up so we have the x and y is equal to the constant, such as here. We have two equations. We have ax plus by is equal to c, and dx plus ey is equal to f. So here are constants, and then along here we've got x and y. So you've got here x and y, and so it doesn't matter which one you put first, either the y term or the x term, as long as you put the x terms for both equations at the front, or the y terms at both equations at the front. So what I mean by that is ax plus by is fine, by plus ax is fine, but if you do this method, put these terms in this order, then you have to have ey plus dx. So you have to continue the same order for the other simultaneous equation, for the other linear equation as well, when you set up the simultaneous linear equations. So if we have ax plus by is equal to c, then dx plus ey is equal to f. Now we can represent this linear system using matrices. We can do that by going A, B, D, E, X, Y. And if you times these out, we get on the top, this is equal to AX plus BY, which is here, and on the bottom, DX plus EY. So you can see how this is the same as this terms here. But now this is equal to the constant, so that's why we just put in the constant, C, and F. So we can set it up so this and these two are equivalent. So we've got this form A, B, D, E, X, Y is equal to CF. Now you don't need to know too much into the technicalities, but when this term here has an inverse, then you can cancel sort of them out, then move this inverse to the other side. And then when there's an inverse on the other side, there will be a unique solution. So when the determinant is not equal to 0, then it has an inverse. It has an inverse. But basically what you need to know is that when the determinant does not equal 0, it has a unique solution, this simultaneous equations. And when it does equal 0, so when the determinant doesn't equal 0, it's unique. And when the determinant does equal 0, then it is either many solutions or none. And we have to do it further. Then we have to look back at these equations and see which one it is. And the way we can do that once we look at this is that when there is many, they are the same. So this will become a bit clearer once we look at an example. So here we have find the values of k for when there is a unique solution, no solution, and infinitely many solutions. So this is with the simultaneous equations y minus kx is equal to 5 and y minus 3x is equal to 2k. Now this method is easiest, well this is a bit easier because to change into the form y equals mx plus c if we're doing the other method. However, sometimes if it's automatically in this form, it's easier to do the matrix method. As changing it over, sometimes you get fractions and it may be getting a bit complicated. We don't need to worry about that at the moment. So we have y minus kx equals 5, y minus 3x is equal to 2k. So first thing to check, are the y and the k in the same position? Yes, they are, so that's fine. So we can represent this linear system by going 1 minus k, 1 minus 3, xy is equal to 5, 2k. Now, if we want to find a unique solution, that's when the determinant does not equal 0. So the determinant of this term is equal to AD minus BC, which is equal to negative 3 plus K. So we don't want it to equal 0. Therefore, K does not equal 3. And as you remember, with unique solutions, we don't care about the translations, so we don't even have to worry about what the constants are. So therefore, for unique solution, we just say K cannot equal 3. So therefore, K is all real values apart from 3. Now we need to look at no solution or infinitely many solutions. So with the no solution, it's the same thing in infinitely many solutions. We have to let the determinant equal 0 now. So that means we had negative 3 plus K has to equal 0. Therefore, K has to equal 3. That means when we sub this back in, we get y minus 3x is equal to 5, and y minus 3x is equal to 6. So we can see that these equations are different, and because they are different, there's not going to be infinitely many solutions. So as the gradients are the same, the translations are different, the constants are different, therefore there will be no solutions when K is equal to 3. Now for infinitely many solutions, this can't occur. And the reason why this can't occur is because when K is equal to anything apart from 3, we have a unique solution. When K is equal to 3, then we have no solutions. And this can occur, this typically does occur, like one of them can't occur when we just have one variable. So here we have one variable, but a previous question we looked at, we had 2 variables. But the main thing with this matrix method is to set up the equation, and then you have to know for when the determinant it doesn't equal 0, that's for unique. And then when the determinant is equal to 0, that's for many solutions or infinitely many solutions or none. And to work out which one it is, the many is when they are the same. So the exact equations are the exact same. So you look at the constants, and then the none, they are different. So going on to another example, here we have the simultaneous equation. So mx plus 8y is equal to 8, then 8x plus my is equal to m. So we're going to look for unique solution, many solutions, and no solutions. So firstly, set this up as a matrix. So m, 8, 8, m, x, y is equal to 8m. So for a unique solution, the determinant cannot equal 0. That we've worked out the determinant is m squared plus 64 cannot equal 0. Therefore, m squared cannot equal negative 64. Yeah, I made a mistake here. So obviously m squared cannot equal negative 64. So it's the determinant is equal to AD minus BC. So it's a minus there, so it's going to be minus 64. So m squared cannot equal 64. Therefore, m cannot equal plus or minus 8. So what we can do then is to say for a unique solution, m can be any real value apart from negative 8 and 8. Then what about for many solutions? So we've already set up this equation. Now, with many solutions, the determinant has to equal 0. Therefore, for b, the determinant has to equal 0. Therefore, m has to equal plus or minus 8, because we've just done that calculation. But if we sub this in, let's see what happens when m equals negative 8. When m equals negative 8, we get negative 8x plus 8y is equal to 8. Then 8x minus 8y is equal to negative 8. Now these are not the same, so therefore they're not many solutions or infinitely many solutions, because that's when the equations are the same. But when n equals 8, that does occur. So when m equals 8, you have 8x plus 8y equals 8 twice. Therefore, so like many solutions occur or so when many or infinite occur when m is equal to 8. Then what about no solutions? Well, no solutions occur when the determinant is equal to 0, so that's m equals plus or minus 8. Then we have to sub that back in to see if it's many solutions or no solutions. We found that when m equals 8, that was infinite, but when m equals negative 8, the equations were different. Therefore, there are no solutions when m is equal to negative 8.